Hello everyone. Now we will discuss on the topic solid waste and hazardous waste management part 3, and we will be focusing on the gasification. The contents are definition and basic chemistry of gasification, gasification reaction schemes and steps, syngas production and efficiency, factors influencing gasification, advantages of gasification, typical process flow sheet and utilization schemes for gasification products, syngas cooling, conditioning and cleanup, gasifier types, gasifiers for biomass and mists, advanced gasification, plasma gasification process, some biomass and waste gasification plants, and comparison between incineration and gasification. Now, we will see what the gasification is. Okay. So, unlike incineration, in this method we will be providing controlled amount of oxygen. So, feedstock will be there, controlled amount of oxygen, and steam is required also for this gasification, but if the feedstock contains very high amount of moisture, then the steam requirement may not be needed. So, gasification is a process that converts carbonaceous feedstocks including biomass and waste into combustible gases containing hydrogen, CO, CO2 and CH4 basically, with specific heating values in the presence of partial oxygen supply. Typically 35% of the oxygen demands for complete combustion and or suitable oxidants such as steam. The produced gas is called as synthesis gas or syngas. When the waste and biomass is reacted with oxygen and steam, so this is called as syngas. But when the air will be used in place of oxygen, then nitrogen will also be available in the product, and that gas is called as producer gas. So, syngas can be used for various applications including liquid fuels, diesel and gasoline production through Fischer-Tropsch synthesis. So, that is one advantage of this. So, we can get from solid fuel to liquid fuel also through this route, and if air is used in place of oxygen, the produced gas contains high amount of nitrogen and it is termed as the producer gas. So, we will see the basic chemistry of the gasification process. So, one, in this process we have carbonaceous feedstock. So, carbonaceous feedstocks and oxygen and steam will be needed, and somewhere steam may not be needed when sufficient moisture is available in the feedstock itself. So, what will be the reactions? The elementary reactions which we can propose, that C plus half O2, that is CO, the carbon monoxide is produced through these reactions where del H is minus 110.5 kilojoule per mole, and there may be some combustion. So, this reaction C plus half O2 CO, that is called gasification with oxygen, and combustion with oxygen, that means complete combustion, that is with stoichiometric ratio of oxygen. So, that is CO2, and gasification with carbon dioxide C plus CO2, again 2 CO, and then gasification with steam. So, C plus steam which is available or provided, so that is CO plus H2, these are the products, and gasification with hydrogen. So, this hydrogen which is produced from this reaction, the gasification with steam, so that hydrogen can react with the char and can give us the methane. These are the main reactions which are proposed to be involved in the gasification reactions, and there are some other reactions, that is side reactions like CO plus H2O, that is H2 plus CO2, that is water gas shift reactions, and CO plus 3H2 CH4 plus H2O, that is methanation. So, these are the different reactions which have been proposed to be available during the gasification. These are the elementary reactions, and del H values are also given for different reactions. So, this reaction gasification with carbon dioxide, that is also called Woodward reaction, and this is endothermic reaction. So, it is clear from this that both endothermic and exothermic reactions take place during the gasification process, and we have also discussed that if we use oxygen we will get syngas, and if we use air we will get producer gas. Now, we will see the difference in composition between these two gas types. So, type, that is typical major compositions like say hydrogen, CO, CO2, CH4, heavier hydrocarbon, nitrogen, water vapor, and also the typical heating value if we compare. So, hydrogen in case of syngas 20 to 30%, whereas producer gas 13 to 19%. and CO 40 to 60%, here 18 to 22%, and CO2 5 to 15, where it is 9 to 12, and CH4 0 to 5, here 1 to 5%. Heavier hydrocarbon, it is present in producer gas, and nitrogen content is very high in case of producer gas, but here it is less, and water vapor is also here 8 to 12% for syngas and 4% around for producer gas, and typical heating value is 9.3 to 14.9 megajoule per meter cube, whereas it is for producer gas it is 4.5 to 6 megajoule per meter cube. So, these are the different properties of the syngas and producer gas. So, accordingly we can select their application. Now, what elementary reactions we have proposed, we have seen in the previous slide for the gasification reaction, that may not be exactly representing the overall reactions, because the feedstock will also contain ash material, sulfur and other materials also, nitrogen etcetera, which was not considered during those elementary reactions. So, people tried to develop some new mechanism or reaction schemes to explain the gasification reactions, like say feedstocks is initially heated, and it is proposed that the char and volatiles are produced in the first step, then in the second step both char and volatiles are gasified. So, gasification of char and gasification of volatiles takes place and gives the syngas. So, when the two intermediate products we are getting, so different researchers proposed the different reaction schemes for the production of the syngas through these volatiles and char. For example, for gasification of volatiles like CnHm plus half NO2, that can give us half MH2 plus NCO, and for char gasification CHXOI char plus 1 minus YH2O, that gives X by 2 plus 1 minus YH2 plus CO. So, these are different types of mechanism or schemes have been proposed by some researchers here Smoot and Smith in 1989. Hereafter, after that some more comprehensive mechanism or schemes have been proposed by some other researchers, those can be used for more comprehensive understanding of the process, which may be available in other references. So, now we will see what are the steps involved in a gasification process. Basically, in gasification process like incineration process, here also the drying, devolatilization, oxidations and this ash cooling are also taking place. Okay. So, drying, pyrolysis, reductions, oxidation, all those reactions take place during the gasification. We have also mentioned in our previous slide as well. So, this is one example of say fixed bed gasifier. So, our feed is coming from the top and from the bottom steam and oxygen or air is sent. So, there is a grate where the solids will be, the feedstock will be stored. Basically, after combustion the ash will be coming at the bottom and some feed will also be available here. The oxygen is provided here, maximum oxygen is there. So, feed will be oxidized initially. When the gas stream will goes up, the availability of oxygen will reduce. So, reduction will start, oxidation will be subsided, and then reduction will be started, and then there will be only heating. So, pyrolysis and then only drying, moisture removal, and gas will be going out from the top. So, this is one scheme for the gasifications in the reactor, and drying, devolatilization, oxidations and ash coolings are very important, where the ash is coming out from this through the grate, the ash will come down and it will be collected and it will be cooled and managed through a proper route. And unlike incineration, in case of gasification the volatilized gases do not get burned. So, this gas which is volatilized here, that does not get burnt, that is why the CO and H2 containing syngas we get, and chars also get gasified as oxygen supply is less. We have already discussed in the previous slide also. Now, we will see how can we predict the fuel gas production. If we know the rate of feedstocks utilization, on that basis, and if we know the air flow rate, then on that basis we can calculate the fuel gas production, that is say producer gas production rate normal meter cube per kg. So, syngas production can be determined if air flow rate, feeding rate and composition of syngas is known. If a waste is composed of carbon hydrogen only and syngas contains CO2, H2, CH4 and C2H2, the syngas production can be related with this formula. So, this formula is derived on the basis of nitrogen balance. You see what are the nitrogen present in the air flow rate into 0.79, assuming that 79% is nitrogen. So, that is the nitrogen present in the air. So, that nitrogen will be available in the fuel gas. So, what will be the rate of fuel gas? That one into the nitrogen content in the fuel gas, that is 1 minus sum of this gas divided by 100. Okay. So, that is the nothing but the fraction of nitrogen present in it, and then feed rate. So, per unit feed rate, what is the fuel gas production, that we can get by this expression. So, this is the air flow rate into normal meter cube per second into 0.79 divided by 1 minus CO plus CO2 plus H2 plus CH4 plus C2H2 by 100 into feeding rate of this solid material. So, that is in kg per second. So, that way this expression is coming by the nitrogen balance in air and in the syngas. And we also predict or calculate the yield of hydrogen and CO like this expression. Hydrogen yield is hydrogen atom in the syngas divided by hydrogen atom injected, and CO yield is carbon atom in the formed CO by CO atom injected. So, that way we can calculate the yield of CO and H2. Now, we will see the thermal efficiency. In case of gasification, the thermal efficiency can be defined as the energy efficiency of the process or cold gas efficiency is defined by the ratio of the LHV of cold gas to the LHV of waste treated. LHV is low heating value and incremented by the added energy, that is electric or fuel for allothermal processes per kg of waste. So, efficiency is equal to LHV of cold gas, that is kilojoule per normal meter cube into fuel gas production normal meter cube per kg by LHV of waste treated, that is kilojoule per kg, plus allothermal power kilowatt per waste flow rate, that is kg per second. So, this allothermal power, that means the additional energy which is needed for the conversion of the feedstock to the product. So, this is the relationship of the energy efficiency. Generally, the conversion efficiency of thermal power plant is between 30% and 40% of a single cycle steam power plant and can be up to 60% for a combined cycle gas turbine power plant. So, we have either combined cycle or bottoming cycle or topping cycle. So, there are different types of thermodynamic cycles which are applicable for the recovery of energy in a thermal power plant. So, these are the typical efficiency for different types of thermodynamic cycles applicable in the thermal power plant. Now, factors which influence the gasification, that we will discuss. So, the type of feed injection, what type of feed we are using, that will influence the syngas production. The gasification agent used, whether we are using air or oxygen. Type of heating, it can be done either by partial combustion of the biomass in the gasifier, that is directly heating, or from an external source indirectly heating, such as circulation of an inert material. The temperature range also influences the performance of the process. The pressure range under which the gasifier is operated, that is also important for the performance of the gasifier. And this gasification process has some advantage over the incineration process, like say reduced carbon dioxide emissions and then compact equipment requirements with a relatively small footprint, accurate combustion control and high thermal efficiency. So, these are the reasons why the gasification is preferred. Moreover, the products can be used for different applications. Now, we will see the flow sheet and utilization schemes of gasification products. So, we have waste and biomass. So, that will be after pre-treatment going to gasifier, that means some pre-treatment is retained to make it suitable for applications in the gasifiers. That means, it may be needed to densify, to increase its density, it may be required to grind it to have a particular particle size. So, that can be needed for the effective operations in the gasifier, and then we will be sending the oxygen or if needed steam. So, then the gasification will take place. So, syngas will go out. So, if we supply oxygen, then we will get syngas. So, syngas will be having some particulate matters. So, that stage 1 clean syngas cleanup. So, that particulate removal. Okay. So, cleaning residues is coming here. Then second step syngas cleanup because of the acid gas removal. Okay. So, this also tar removal can also taking place here in this first step, and second step the acid gas removal, that is H2S removal, and then it will be going for this can be used for liquid fuels or chemical synthesis, okay, or it can be used for hydrogen separation, and hydrogen can be used in different applications including fuel cells and can be converted to electrical power, or it can be processed to the gas turbine. So, that we can get electrical power, and followed by waste heat boiler. So, flue gas we can get, and it can be passed to the steam turbine using some additional fuel. It can be going for steam turbine and the electricity production can take place. So, this way the electricity can be produced from the syngas, and then the steam, condensed steam is coming here from the waste heat boiler. So, steam, either steam can come here or this can be going to steam turbine for electrical power production, and in the gasifier we have some residue, that is ash or slag or metals, that has to be managed in a proper way. Now, syngas cooling and conditioning and cleanup. So, syngas which is generated, that will be at higher temperature and it will be containing particulate, it will be containing say acid gases. So, we need to remove this because different downstream applications requires certain level of purification. So, if we see here, so different downstream applications like say power, hydro processing and chemical applications. So, here sulfur requirement is within this limit. Okay. For chemical more purity is required, but for power applications less sulfur removal is needed, and carbon dioxide similarly for power there is no requirement, but for hydro processing more purity is needed. So, less than 0.1 volume percent and 0.05 to 2% volume percent carbon dioxide is needed for chemical synthesis, and CO similarly should be less than 50 W ppm, and H2 CO control as per requirement for the type of chemical we are interested to produce. So, this table clearly indicates that the syngas requires some cleanup for its downstream application, and the cleanup is needed to reduce syngas temperature, extract valuable energy, use conventional and commercial processes that can be used in commercial and industrial processes. This also remove chemical species that foul, corrode or erode system components, poison or deactivate chemical processing agents and are environmentally unacceptable for release, and target syngas purity, H2S and CS concentration, CO2 concentration, and these are as per this table, and H2 CO ratio has to be adjusted for the application in chemical synthesis route. Now, major types of gasifiers for coal and pet coke. So, biomass and waste are basically low dense materials, highly reactive materials, but coal and pet coke are less reactive and dense material, the carbon content is higher in this feedstock. So, these reactor for the gasification of this type of feedstocks require higher temperature, and we also know that pet coke is produced as the residue in the petroleum refinery. So, that is a waste material, waste product. So, this is also important feedstock or waste material for the production of energy. So, if we see different types of reactors which are used for the gasification of coal and pet coke, then we see those are basically moving bed or fixed bed, both are same. Some books it is mentioned as moving bed and some books it is called as fixed bed, some is fluidized bed and another is your entrained bed. So, these three basic type of reactors have been used in literature for the gasification of the pet coke and coal. This is your fixed bed or moving bed. So, why moving bed? So, this is a grate and then the coal is coming from the top and from the bottom steam and oxygen air and is entering, and from the top gas is going out, ash is getting out, which is passing through the grates and then it is coming through this the bottom part. Okay. So, here the material is fixed here, the bed is fixed, the coal is coming from the top and from the bottom the ashes are going out. So, this is a fixed bed. Why it is a moving bed? The coal is moving from top to bottom. So, that is also this is also moving bed also, but in fluidized bed the coal is put from the top and from the bottom steam, oxygen and air is sent, and then from the top again the gas is going. But in entrained bed coal, steam, oxygen, air all are entering at the top, and from the bottom the slag, and from the bottom side we are getting the gas. So, if we see when the oxidation is there, then there will be the maximum temperature. So, in this type of reactions along the height, if we take the temperature, then maximum temperature will be the middle of that, okay, that will be around 1800 degree centigrade. Okay. So, this is maximum temperature, but that in this case in entrained bed throughout the length we are getting high temperature, and in the fluidized bed we are getting maximum temperature at this part not. So, that these are the different temperature distribution in different type of gasifiers. So, the type of gasifiers will help to get different type of temperature distribution along the length of the gasifier, and that will also influence the performance of the gasifier, and it can also help us to decide which type of gasifier will be more suitable for handling what type of feedstocks. Like say for entrained bed we are getting throughout the whole length we are getting very high temperature. So, if the material is less reactive, then also those material can be suitable here for gasification. That is why petcoke is more suitable here, but for biomass and waste. So, since the materials are highly reactive and less dense, so we do not need this much of high temperature and this type of arrangement. So, our fluidized bed or fixed bed can be a suitable option. Now, gasifier for biomass and wastes, if we see basically fixed bed, fluidized bed have been used, entrained bed has also been used, and another gasifier, that is plasma gasifier, has also been reported. So, fixed bed are basically updraft and downdraft. So, this is our updraft type. So, biomass is entering from the top and from the bottom we are sending air or oxygen and steam, and then gas is going out from the top, and from the bottom we are getting the ash. So, this fresh feed is added to the top of the bed while air enters through the bottom. So, counter current flow. So, this approach was developed at Georgia Institute of Technology, and syngas contains about 25% water insoluble tars, simple and inexpensive process. So, this is the main disadvantage, that it contains good amount of tar in the syngas, and exit gas temperature about 250 degree centigrade, combustion zone 1000 degree centigrade, operates satisfactory under pressure, high carbon conversions and thermal efficiency, low dust levels in gas, potential for channeling, bridging and clinkering. Then we see the downdraft. So, in that case biomass from the top and air oxygen from the side. So, it is gas is also from the bottom part. So, that is a downdraft, gas is coming from the bottom and steam is also from the side. So, feed enters at top and air from the sides. Concurrent flow fixed bed gasifier, both are in the same direction, solid and the oxidizing agent. So, suitable for dense high quality feedstock such as briquettes, hog fuel or high quality wood chips, suitable for small scale engine applications. Both pyrolysis products and oxygen are free to react with the charcoal. Tar content in syngas is lesser than updraft. So, updraft has more char content than the downdraft gasification, and the feedstock for these gasifiers should have low moisture and ash contents or high ash sintering temperatures, very low fines contents, limits to scale up capacity and potential for bridging and clinkering. It has some potential for bridging and clinkering. Now, we will see the fluidized bed gasifier. So, here again the biomass from the side and from the bottom air or oxygen or steam, and from the top syngas is going out. So, this is bubbling fluidized bed and circulating fluidized bed. So, the air or oxygen velocity is maintained in such a way that some solid is also carried over with the syngas and those are settled and recycled. So, that is circulating fluidized bed. And dual fluidized bed, is here, fluidized bed, and that is your bubbling and circulating, both actions are available in this type of reactor. So, here this is combustor and this is gasifier. Okay. So, then air is sent here in the first part, and then second part we are sending the steam. So, configuration is totally different from other two. So, this is dual fluidized bed gasifier is also have been reported in literature, and the feed fluidized in the gasifier, the heat transfer media is required in this case when it is going out. So, we need basically some sand or some other solids. So, which helps for the quick heat transfer purpose. Syngas quality vary widely, high volumetric capacity, flexibility in feed properties, and gasifier temperature may be greater than 500 degree centigrade and less than 900 degree centigrade. So, this is some salient features of this fluidized bed gasifier, and in this case we get high CH4 tar and fine syngas and high carbon in fly ash. These are the negative point. Then entrained bed gasifier. So, like the petcoke gasifier, biomass, oxygen and steam is sent from the top, and from the side we will get the syngas, from the bottom we will get the slag or ash. So, feed air or oxygen and steam are entered from the top and syngas exists at bottom, can be used for large scale plants, requires fine and dry feeds. So, the fine feeds are needed for this purpose. Handling of low density feed in pressurized reactor is difficult. Gasification temperatures in the order of 1100 to 1400 degree centigrade, no tar and less methane and CO2 in syngas. So, this is the one major advantage of it, and slugging potential pretreatment of feed is required. So, since the temperature is very high, the ash may be in slugging stage, and that can be a problem, and temperature of feed is also high. So, that is the disadvantage of it. Another type of gasification is plasma gasification or plasma gasifier, which is used for the gasification of the biomass and waste. So, here high temperature is generated, that is 4000 to 7000 degree centigrade through plasma torch. High quality syngas can be obtained, which can be suitable for all types of waste. This plasma gasification can be suitable for all type of waste. Hazardous compounds are broken down to elemental constituents, acid gas is readily neutralized. So, soluble residues like metals and aggregates, those can be having some market value, and no direct gaseous emissions to the atmosphere, recover fuel value of wastes, heating value of output gas or like electricity input. This ratio if we take heating value of output gas by electricity input, that is equal to 21.4, and residual vitrified mass include inorganics, heavy metals etc., and highly resistant to leaching, no landfill requirement. So, these are the some advantage of this plasma gasifiers. And what the plasma is, if you know that thundering process is one of the example of natural plasma formation. When high voltage is applied across the electrodes, it accelerates free electrons. The energized electrons ultimately collide with and ionize, dissociate or excite the ambient molecules, thus producing more free electrons, and finally an electron avalanche called a streamer, which further propagates and form a spark or arc. So, this is a plasma arc. So, torch power levels from 100 kilowatt to 200 megawatt and produce energy densities up to 100 megawatt per meter cube. The high energy electrons can work on all types of molecules and create radicals such as this oxygen radical, OH radical, nitrogen, and indirectly H2O2, O3 and others. So, all these radicals start chemical reactions to form final products. For carbonaceous materials, CO and H2 becomes major share in the produced gas in case of gasification. Now, we will see the difference in the properties of feedstocks for different types of gasifiers, like say fixed bed gasifier, fluidized bed gasifier, that is bubble column and bubbling fluidized bed and circulatory fluidized bed, entrained bed and plasma. So, you see the typical particle size is 50 to 150 mm and moisture content 10 to 60% for fixed bed gasifier, whereas for fluidized bed particle size less than 50 to 150 mm, moisture content 10 to 55%, and fluidized bed circulatory, the particle size less than 20 millimeter and moisture 5 to 60%. For entrained bed, particle size less than 1 millimeter and moisture 15%. So, in case of moisture entrained bed, the particle size requirement is the minimum. So, the smallest particle size are required, but for plasma these are not important. So, plasma gasification can be used for variety of wastes, and for entrained bed gasifier some pretreatment steps are needed because thus very small size is required. These are some important technology licensors for different types of gasifiers like entrained bed gasifiers, bubbling fluidized bed, circulating fluidized bed, plasma gasifiers. So, you see here different technology licensors, and most of the above biomass gasifier development started after 1980, and up to 2010 maximum capacity of a plant was below 500 ton per day oven dry basis, and plant capacity increases up to 3000 TPD after 2010. So, this has we have got it from this reference, and now we will see the different plants, okay, some biomass and waste gasification plants around the globe. So, Australia, Brazil, Canada, Germany, Sweden, different countries, different plant, different feedstocks, different products, and syngas cleaning options are also different, and year of commissioning are also provided in this slide. And here we will see the difference between the gasification and combustion. So, if we take some criteria, that is purpose, process type, raw gas and utilization, solid products and handling, and pressure, then you see the for gasification generation of valuable gaseous products, it is our purpose, and for combustion generation of heat or destruction of waste is our main purpose, and thermal and chemical conversion using limited oxygen is our process type, and here we get complete combustions with excess air or oxygen. And then raw gas and utilization, you see these are the raw gas which contains H2, CO, H2S, NH3, particulate matter and heat electricity chemicals we can get from it, whereas in this case there is no CO basically, and NH3 is converted to NOx, PM, SO2 etcetera is there, H2S is converted to SO2. So, these are the basic difference in these combustions and gasification process, and it is only used for heat and electricity, it cannot give us any chemicals or hydrogen. So, solid products and handling, then char or slag is produced in this case. So, char is fuel and slag is construction materials. Here we can get bottom and fly ashes. So, landfilling or sold as a material for making concrete, and pressure atmospheric to high pressure the gasification reaction can take place, but combustion takes place in atmospheric pressure. So, up to this in this class, thank you very much for your patience.